Today we're going to shift from sample preparation to more of the electron tomography data collection pipeline. And our first speaker is Misha, staff scientist here at NYSBC. What is your favorite part of the CryoET workflow?
Data acquisition.
Data acquisition. Do you have a favorite instrument?
Well, curious. Yeah.
Very good.
Hi, good morning. Hope you had coffee. I'm still working on mine, so I'll be a little bit choppy probably. But we'll talk about my favorite part of CryoET, so CryoET data acquisition. In the recent times, I don't do a lot of CryoET data acquisition. So we have other people as instructors here and part of this group who are doing a lot of data collection, and we'll look at the actual setup of our instruments later in the day today, and Stefan is here. So it's going to be between Stefan and me and a couple other people to actually show how we do it here. And next slide doesn't work. All right, so I want to open up to the tomography state of the field, kind of to remind you why we all gathered here. First of all, finally everything's figured out. Everyone agrees on best practices. All settings, acquisition platforms, everything is fully unified, and we have standard settings set up that we can apply to 100% of all the sessions. And finally, data processing is a breeze. Everything's set from coordinate system, image format, subvolume refinement, everything is well coordinated and applied universally, making data processing essentially a breeze. And finally, happy April Fool's Day. So this is not true, but this is the dream, right? And some of these things cannot be really achieved in tomography just because the way you set up the instruments, the way you prepare the sample will influence what you get in the end. Another way around, if you know what you want to get in the end, if you know the answer, or at least how the answer should look like, this will influence how you're setting up your session, how you're setting up your processing, and how you're setting up your data acquisition. So I'm more experienced with data acquisition. But this is sort of what you want to get in the middle of your data acquisition. This is still series on the left. So we collect multiple images from different angles, usually in about 3-degree steps, 2-degree steps. This is some bacteria doing something in the middle there, excreting some vesicles. And then once we have all these tilt series, we need to figure out exact geometry at which we acquire them. And once we know what is their orientation in 3D space was, we can back project them and create reconstructions. So this is the intermediate goal for all the tomography. We want to get the thing on the right. The left is the flat images, we call it tilt series, the series of tilts, and on the right is a reconstruction, which is the back projected tilt series images. And I'm saying this is an intermediate goal because you have to get this. Until you get this, you cannot do anything else in tomography. But data processing, this is just the very, very beginning. But something like this is a very useful feedback that you can get, and you should get on the fly or very fast after you concluded your acquisition sessions to see how your data looks. And one thing I'll note, and I'll talk about this later, you can see in the later tilts, familiar with gain artifacts, you'll see a stripe going through the image, and that's because it's very slow to zoom. But you can see gain artifacts in higher tilts, and that's because your specimen, this is from a lamella, gets very thick. And you really can't set up your camera to be in the perfect dose rate for it in both low tilts and high tilts, just because its dynamic range cannot just cover it. So you always have to choose the best optimal setting for your data acquisition. All right, so how does the pipeline actually work? So you start with your favorite bug. Thank you, AI, for drawing this. Whatever that might be, your favorite virus, your favorite, I don't know, HeLa cell. Then you do tomography, and then at the end you get your reconstruction at whatever resolution. And as I was mentioning, what you want to get in the end, you better know the answer, at least how the answer looks, so you can get through all of this and adjust all the settings. This is sort of the settings you have to keep in mind. I kind of arrange them from sample prep all the way to data processing. It's not exhaustive. And what you see in the end in black is what I consider kind of figured out. We know what we're doing. And any staff scientist here who does tomography can answer the questions about these things. Blue is, we know how to do it, but there are a lot of variables. And at least for me, the red is, I don't really know if I can do it by myself. So I've done some bit milling, but I think there are so many more parameters that change in bit milling, and especially in data processing later in the day. But thankfully for me, we'll be talking more about the middle part, which I think not only figured out, but I understand pretty well. All right, so I'll split it into two parts: the hardware setup, which is your microscope. We're a TFS facility. Thank you, TFS, for sponsoring. Thank you for coming. So mostly what we'll talk about is the Thermo Fisher instruments. And the session setup, which mostly will be dealing with the software. We use predominantly serial EM for data acquisition, but we also switch into using Tomo 5, also by Thermo Fisher. All right, so the choice of hardware. There are multiple platforms we can use, but we mostly stick with the Thermo Fisher stuff. So we have Krios G4, one. We have several that probably can give you the better answer. We have several G3Is, and we have Glaciuses. We don't have Joules on site, but those are also viable instruments for data collection. Never use them, so can't comment. And the difference between 300 to 200 kilovolts, despite, well, there's price difference, well, twofold. And then the mean free path in 300 kilovolt is much longer, which means you can look through thicker stuff, and your camera will be more happy to look at your data, because now you can maintain the dose rate that the camera is designed for thicker specimens. And if you're dealing with lamellas, even if you're milling at, say, 150 nanometer lamella at 60-degree tilt, it will be already approaching the mean free path of 320 nanometers. At 60-degree tilts, the 150 nanometer lamella becomes 300 nanometer lamella. So Glaciuses can also be used for this, but the mean free path is short. So we choose these mostly for our hardware, and of course they should be equipped with energy filter. So energy filter will filter out the electrons that are not yet considered useful in data acquisition, the inelastically scattered electrons. So in the normal way, you have the lamella, you shoot your electrons and you collect all the electrons on the camera. The camera is actually happy because it maintains the dose rate, because all the electrons that went through will be collected, elastic and inelastic. With energy filter, you will filter out some of the electrons, and depending on the thickness of your eyes, it can be a lot, it can be a little. But now that can make camera unhappy. You can start seeing gain artifacts if your sample gets too thick. But it increases your contrast dramatically. All the electrons that don't contribute to contrast are now gone, and now your tomography has very high contrast. And especially, again, for thicker samples, it's critical because all you will see in without energy filter is you just losing the features, they just start disappearing into the noise. Well, with energy filter, you'll still maintain contrast. The precision, how stringent you are filtering, is set by the energy filter slit width. And that's one of the more standard settings, depending on the instrument you're using. And yeah, it's kind of default. We usually use about 15 EV or 20 EV for Krioses equipped with G10 energy filter. Yeah, so as I was mentioning, in thicker eyes, the dose rate can drop to 10% of the original. You set it up to collect the 30 electrons per pixel per second. It can drop all the way to 3. And then, of course, you'll have some artifacts in your images. One of the very important things is pixel size. And again, you need to know the answer. You need, or at least to get an idea of how your answer might look like to actually set up your session. There's a very big difference between 1.3 angstrom per pixel and 3.6. And that will influence different parameters. Of course, it will influence your theoretical achievable resolution. So if you're going for high resolution, if you're one of those people who wants to get 3 angstrom structure from your tomography data, good luck. Then you probably have to collect at 1.3 angstrom per pixel. If you're doing segmentation, probably 3.6 is good enough because that will increase your field of view, will lower your highest possible resolution due to Nyquist limitations. But it will also, the larger the pixel size, the better will be your tracking accuracy. And there are some other beam settings that can be influenced by the pixel size. For comparison, here's some yeast. And I think this is relatively to scale. So that's field of view at 1.3 angstrom per pixel, 2.1 angstrom per pixel, and 3.6 angstrom per pixel. So your pixel went in size little bit over the double, but your field of view increased as a square of that because of that's how rectangles work. And you can see that the amount of data you will get at larger pixel size is just insanely huge comparing collecting 1.3. So especially if you're earlier in the process, you want to learn your specimen, you want to know, how your data looks. Start at a larger pixel size. Start at a large field of view. Collect big fields of view. Collect the data, process it, look at it, and see. Okay, if you hit in Nyquist, lucky you. Then drop the pixels and go collect small. A lot of things also go into this about dose. So I was mentioning dose on the camera. There are 4 doses we talk about. Dose rate, which is the amount of electrons your gun essentially spits towards the camera. And there's dose per tilt series, which is the total electron dose accumulated as a radiation damage on your tilt series. Then dose per tilt image, so that's the individual tilt, and of course dose per frame. And all of these parameters are important and they're more or less standardized, so we keep the dose rate in 16 and 32 for K10, K3 cameras. Dose per tilt series, keeping around 100 electrons per angstrom squared, so that's the total dose for the specimen. Total tilt image between 2 and 5, and dose per frame about 0.2 to 0.5. The limitation here, why do we have to keep this dose so low and consecutively this dose so low for the individual images is because of radiation damage. If you put too much electrons, your sample will most likely start bubbling. Especially if you're looking at cells, your membranes will start bubbling at around 100 electrons. So, and it doesn't matter how slow you go, what your tilt scheme is, it just at 100 you'll see formation of probably hydrogen bubbles in your sample, especially around the membranes. Next is beam size, especially for newer people who are here. You think you have a lamella and you can image everything in a lamella. You can't. And one of the reasons why is because at 60 degrees tilt, despite your camera size and the beam size remaining the same, you will be, you now will be damaging areas that you were not damaging before. So at 0 tilt, you're damaging somewhere between these 2 cells, and this knob of the membrane is undamaged. But here at 60 degree tilt, that knob is also receiving radiation damage. And as with single particle in tomography, the first few 0 degree tilts contain high resolution information. So if you already damage that area at 60 degree tilt, even if you collected only 1 image there, then you go ahead and start collecting, say, in this area over here, your first few images will still have the dose that you damaged the specimen in the later tilts of the previous data acquisition. So that's one problem. So the area that you imaging will be stretched orthogonal to the tilt axis. And the second problem, you usually need a second tilt series, a tracking tilt series, and in this case, we can put it somewhere in a nonsense region, hopefully for work. This is the tracking. So you don't want to adjust your parameters because of stage imprecision. You need the tracking tilt series, and you don't want to track where you image. So that you have to separate the tracking area from data acquisition area, and this is the classical way of doing it. For every acquisition area, you have 1 tracking area. There are ways around it, but keep that in mind that only a quarter of your lamella with this setup can be imaged. So let's go to software. So there are many choices available to you. 3. And recently, I don't know the state of the development of Leginon. We use the Leginon a lot for single particle, and we love it. It's great. It has a database. Everything's connected, convenient, and easy to understand. But tomography development, I think, pretty much stopped on it. So we're actually down to 2 choices, and both of them are great choices. Thermo Fisher Tomo 5, recent updates make setting up everything very fast and easy. If you use EPU, you will be familiar with Tomo 5 in a few hours. And of course, Serial EM is a very flexible platform that's been in development since, I don't know, 18th century, because the glue still looks like that. And yeah, it's very flexible, and there are recent developments that make CryoEM a very good choice for data acquisition tomorrow. So I'll talk a little bit about CryoEM, and we'll demo CryoEM today. And what makes it very appealing is this case developed by Fabian. And the recent update is called SPACE, where S stands for smart, and PACE stands for, I don't remember the acronym, but it stands for parallel data collection. So in the classic way of collecting data, as I mentioned, you will have your acquisition tilt series and tracking tilt series. And then if you want to collect more data, you will move say, above it, further away on undamaged region, and start collecting there, but you'll need another tracking tilt series. This is rather slow because you only collect one tilt series at a time. But in space mode or pace mode, you only have one track and tilt series, and you just image shift to every other area on the lamella, at least increasing the amount data you can collect by 50%, the amount of accessible data, because now you do not need an independent tracking tilt series for each acquisition area. And the same goes for TOMO 5. So this is also implemented in TOMO 5, and from what I heard, works reasonably well. One thing you have to keep in mind for this, you need very accurate geometry estimation of your sample. So if this is a lamella, it's a 20-degree pre-tilt, and also it has some in-plane rotation depending on how you loaded the grid into the microscope. So you have to estimate those parameters so that the PACE software knows exactly the geometry of the sample so it can start tilting. The reason for that is that if you tilt and say this is the top of the lamella, it will be going away from you. This is the bottom of the lamella, and that's the tilt axis, so this will be coming towards you. If that happens, the defocus here will be decreasing, the defocus here will be increasing, the defocus in the middle will stay unchanged. So you need to know the geometry to correct for that change in defocus due to tilt, because the top and the bottom of lamella are very different. But it's very, very fast. So in classic way, it's about 15 minutes per tilt series, and half of the usable area is destroyed because you need to track somewhere. In pace mode, it takes time to get things going, especially for lamella, without using the S part of pace. You have to image shift to each target individually at high magnification and confirm that you're there and record the image shifts, but your accuracy becomes 100% because you're going to be exactly targeting the feature that you want. So it takes time to set up, but it's very precise and very accurate. So the way it does things, records tracking image, adjusts image shift, records acquisition target, and goes to the next one. Here it does all of the same thing, but it image shifts for every single target in the group. So it adjusts the image shifts based on the tracking tilt series, adjusts the image shift matrix, takes the geometry into account, and then image shifts and acquire every single tilt axis. The time it takes to do this is approximately the same. It's about 15 minutes per tilt series, but you're collecting multiple of image. So it will be, say, 15 minutes or 20 minutes per tilt group. Finally, let's talk a little bit about the tilt scheme. Nobody uses these anymore, really, the swing and bidirectional. You still can. If you want to collect some data really, really fast, you can do swing. So you start at, say, -45, and you collect without stopping all the way to 45 degrees. If you really want to go for speed, from the very good tracking, but you're starting at very high angle, it means you're going to be looking at a very thick sample, and your high resolution information will be going through much bigger eyes than it should be. So this is not a good idea. You always have to start around 0. So that's the bidirectional. You start at 0 and go all the way to positive side, and then go back to 0, go all the way to negative side. That's the classic way of doing tomography. Gives pretty good results, good tracking, good speed. And the slowest way to do this is dose symmetric, where you collect few angles to the right, few angles to the left, few angles to the right, few angles to the left. This distributes your dose at lower tilts most efficiently. So you're imaging the thinnest possible eyes, and you're getting the lowest damaged images. So you're getting, from these tilts, you're getting the highest resolution, especially the first, say, 7 tilts. But it's much slower. But if you combine this with pace, that you tilt stage multiple times into different directions, but you can collect multiple tilt series at the same time, actually the speed becomes very, very good. Yeah, tilt range. So for pattern grids, I mean, if you're doing tomography on just some complex that has severe preferred orientation, it just needs tomography, or you purified mitochondria and you're putting it on pattern grids, you can go all the way from -60 to 60. There's no problem. The stages can tolerate that, and you have very good coverage and very small missing wedge. You start at 0 stage tilt, go at 3 degrees increment will be good. So for lamella, it's a little bit different because the second thing you have to take into account is that the lamella itself is tilted. And depending on the method that you mill lamella, you will have to account for that pre-tilt. So for waffle milling, we usually mill all the way to 20 degrees. That's a lot. So we can not go higher than 60 in one of the directions, because if the lamella is at 20 and you tilt it to 60, then your tilt on the lamella becomes 80 degrees. You will see nothing. It will be just tiny slab of ice that you will not be able to see through. And then on the other side, if you look the other way, you start at -20 on the lamella, and you cannot really go past -60 because the stage becomes very unstable past 60. You can theoretically go to -69, -70, but we usually limit ourselves to 40. So your coverage becomes from -40 to 60 if you're doing the lamella, due to pre-tilt. If you're milling at lower degrees, the 10 degrees, you can do -50 to 60. You can get almost full coverage. So the typical setup for the lamella will be using 300 kilovolt scope. Obviously, fringe-free illumination, because the smaller your beam can be, the less area you will damage without imaging. It's very important. I think every single microscope, or every single piece we have is upgraded to be fringe-free. You don't damage the specimen for no reason. Energy slit for G10, A3 by quantum setup, we keep at 15. Those are at about 24. It will depend on the mag somewhat. If it's a high mag, might be a little bit higher. If it's a low mag, you can drop this lower to keep your exposure reasonably long. 100 micron objective aperture, because you want to squeeze out as much contrast as you can. We use serial, I think it's 4.2. Yeah, with the base. We haven't done the space yet, but we will. Dosimetric tilt scheme as implemented in base, 3 degree tilt increment, and the rest of the dose settings that I described. So about 100 electron total dose, 3 electrons per angstrom per tilt, about 10 frames per tilt. Our standard high mag is 2 angstrom per pixel, but we collect anywhere from 2 to 4, depending on the needs, depending on your need. Yeah, and that's all I have, and happy to take any questions.
Mentioned that your rules per frame is 0.5.
Yeah.
What does that mean? Like, slash that more.
Yeah, so to do motion correction, because you still have to do motion correction. Like the images we record are still movie stacks, and there will be some drift. To get reasonable motion correction, you need to have sufficient information. So for tomography, we wouldn't do patch correction, we do full frame motion correction. So you can get away with a little bit lower dose, but you still need some to correct for the motion drift. So we keep it about 10 frames for 3 electrons per angstrom squared, which becomes 0.3 electrons per angstrom squared. But since it's a full frame, it's enough information to correct for drift.
For the dosimetric tilt scheme, you just scale that.
Yeah. So you start at the pre-tilt. If you know the 20 degrees, you'll start at -20. And it treats that angle as a new 0. And we also limit the higher tilts. Usually we will do dosimetric for first 10 tilts or something, and then it will swing all the way to the end. Because the whole point of dosimetric is that you collecting high resolution information at your most transparent ice condition.
Ever use like a faceplate?
We did in 2018. Since then, not really. We played with them, and yeah, they provide superior contrast, especially at low resolution, and which was shown very good for tomography. So we can, If somebody has a very specific project, we'll make an exception for them, but usually we don't, and we just use the focus. However, I've heard laser fast plates are coming. That will be easy to use, so yeah, we will go back to laser fast.
Thank Misha one more time.
All right.